To start off chapter 4, let me ask you a question that goes all the way back to the beginning of the course. What is a vector? And more to the point, is a vector an arrow? And if that's really the essence of a vector, then if it's really an arrow, then a column of numbers is sort of a convenient way to describe how the arrow sits in space. Or maybe the column of numbers is really the essence of what a vector is, and an arrow is just a convenient graphical representation of that. I think the more you dive into linear algebra, the more you get the feeling that there might be something else underneath both of those that's really the essence of what a vector is, and that both of these forms are a representation of something deeper. So we are starting to go a little deeper here in chapter 4. And to answer the question of what a vector is, we are going to start by talking about what a vector space is. So let's just dive right into the definition of a vector space. So a vector space has these 10 requirements that have to be true. And this is a step more abstract than you have been before in your mathematical career. Really, we're going to say anything that meets these 10 conditions is a vector space, and the things that live within it are vectors. So the definition here says a vector space is a non-empty, so it's got to have something in it, set of objects called vectors. So there's our definition of a vector, I guess. It's an object. That helps. Really clears it up. On which are defined two operations, addition and multiplication by a scalar, by a real number, and which fits all 10 of these axioms below. And the axioms must hold for every vector in the vector space and for all scalars. So notice anything can be a vector as long as you can add two of them together and as long as you can multiply it by 5 or by a real number. And of course, most of the things that we're going to work with involve like vectors or numbers or x's and y's, very mathematical sorts of things. I think a real abstract mathematician here would like to say, this definition could work just fine for the collection of objects which are all the cars in Mount Vernon, or all the cans in your pantry. Anything, as long as you can say this is what it means to add them, and this is what it means to multiply them by 2. I don't really know what it means to add a couple cars together or to multiply a car by 2. But if you can come up with something, if you can say to add 2 cars together, it means puncture the tires on both of them. Or if you multiply a can in your pantry, that means stack it on top of another can or something. I don't know. That's just random ideas that don't really work. But if you can make up a set of objects, and you can make up something that counts as addition and something that counts as multiplication by scalar, even if it has nothing to do with what you normally think of for addition and scalar multiplication. If you can make up some rules to play by that meet all these conditions below, then you've got a vector space, and the things in it are vectors. So let's take a quick glance through these 10 rules to see what it really takes to qualify for the Vector Space Club. And then we'll look at a couple extensions on these rules, and then in the next video we'll actually get some examples. And I promise this is not going to make a whole lot of sense until we get to the examples. But let's just say that, let's take a quick look through the conditions. So if you have 2 objects in your set, which I will call vectors from here on out. If you've got two vectors, then when you add them, it still has to be in the set, in the non-empty set V of objects. So in other words, if you add two of them together from the set, you still need to get something in the set. So for instance, if I decided that my set V was all numbers less than or equal to 10. And let's say addition, so you have to define your set, right? So there I've defined my set. And you have to define addition, and you have to define scalar multiplication. So I'm just going to say normal addition, so 2 plus 3 is 5, just the way we've always added numbers, and normal scalar multiplication as well. So there's a set of objects. I did define two operations. I just stole two operations, I should say, from what we've always known. Question is this enough to be a vector space over here? So condition number 1 says the sum of two elements from the set, and the way we'll write sum is the normal notation, needs to also be in the set. So that works for some numbers in the set. One number from the set plus another number from the set makes a number from the set. That's great. However, so check mark there, but consider these two numbers from the set. Adding them together makes a number that is not in the set anymore. So number 1 is often called closure. Under addition. And what that means is when you add two things from the set, you don't escape the set. The set is closed. That's not true for my definition over here. I added two things from the set and I ended up outside of the set. So this little definition right here does not produce a vector space. It fails condition number 1. It passes the next couple, by the way. Addition is commutative. So u plus v equals v plus u. That would be true for my little set. And addition is associative. If you're adding three things together, it doesn't matter which order you add them in. That would have also been true for my little set over here. 4 says there's a zero vector. Some object from the set that when you add it to any other object in the set, you get that same object back. That would also be true for my definition. I have a zero vector, happens to be the number 0. 0 plus any number in the set still makes that number in the set. For each u in the set, there's an additive opposite, basically. There's something else called negative u, and when you add them together, you get the zero vector. My little definition breaks there also. Some of the numbers in my set have additive opposites. Boom. 3 and negative 3. That works fine. (10) and negative 10 are both in the set. And you add them together and you get the zero vector. That's fine. But notice my set was all numbers less than or equal to 10. So negative 72 is in my set. But there's nothing in my set I can add to that and get 0. I mean, obviously it'd have to be positive 72, which is not in my set. If I had maybe defined my set to be all numbers between negative 10 and 10, then this one would have worked. Right? Every number in the set would have had an additive opposite. As it is, some of the numbers in my set do not have additive opposites. 6 is closure under scalar multiplication. which means if you multiply any element from your set by a scalar, it's still in the set. And again, notice that's not true for my set. 9 times a scalar like 2. I escaped the set. The set is not closed. 7 says scalar multiplication distributes. 8 says that vector multiplication distributes. In other words, multiplying a vector by 2 scalars distributes. 9 says scalar multiplication is associative. And 10 says that when you multiply by the scalar 1, you still get the same thing back that you started with. All the rest of those would have worked for my set, by the way. So there's only a couple that failed, but as soon as one of them fails, they all fail. So we'll take a look at a couple more examples in the next video of vector spaces. We haven't even seen a successful one yet. All we've seen is my little one that I made up that failed. Actually, let's go ahead and get a successful one right now. Rather than all numbers less than 10, less than or equal to 10, let's just say all real numbers. I think you could probably see that we are now going to pass all 10 of these conditions. The only ones that I failed were because of this less than or equal to 10 restriction. Now I can add any two real numbers together and I'll get another real number. I can multiply any real number by a scalar and get another real number. Every real number is going to have its additive opposite now. So I think that would be pretty good to go. It's kind of a trivial example, but it works for us. Okay, let's talk about a couple more ideas before we close this video out. Let's talk about what we mean by a subspace. So a subspace of a vector space is a subset. So subset just means a smaller collection drawn from the bigger one. And this subspace only needs to have 3 properties. It needs to have the 0 vector, it needs to be closed under addition, and it needs to be closed under multiplication by scalars. So basically, it needs to have oh, I'm on eraser. Sorry, that's why that's not working. It needs to have condition 1, closure under addition. It needs to have condition 6, closure under scalar multiplication, and it needs to have condition 4. And if a subspace meets those 3 conditions, it will be a vector space also. I know that's feels like I'm twisting words around, but consider this legitimate vector space up here. All real numbers, normal addition, normal multiplication. It's a vector space, meets all 10 conditions. Let me make my subspace be just the even numbers. So up here we had all real numbers. Here we have just the even numbers. That is a subset of the real numbers, right? The even numbers. And all even numbers, defined with normal addition, normal multiplication, will be a vector space and meet all 10 of these conditions if they just meet these 3. The other 7 are inherited because they came out of V. Is it true, though, that the 0 vector is in there? 0 is an even number. It divides by 2 evenly. Is it closed under vector addition? In other words, if you add two even numbers together, do you still get an even number? That is also true. Is it closed under multiplication by scalars? If I multiply an even number by, and this has to be any scalar, for each scalar c. There we run into problems. If I multiply an even number by a particular scalar, I get an odd number and I failed. Condition C. So because H, my little subset, which was all even numbers, was not closed under multiplication by scalars, it's not going to be a vector space. It met 9 out of the 10 conditions. It inherited 7 from its sort of parent vector space, and it passed these two, just failed on this one. Okay, that's enough for this video. In the next one, we'll look at one theorem and some examples.